This video is about a paper we published a couple of months ago on the ontological model framework. And if you don't know what that is, it's a framework that has become popular in the past decade to categorize interpretation of quantum mechanics. And what we proved is essentially that the framework has some problem. There are a good subset of models that can't really replicate results from quantum statistical mechanics, quantum information, and quantum thermodynamics. And I think this is an interesting case study if you're interested in foundations to see even essentially how people can get confused if you don't really look at the underlying assumption that you have in a model, you might create some problems. So let's go and look at this result. The paper itself originally was from an idea of Andrea Oldofredi from the philosophy side, and he wanted really to make a small reply to another paper, and the idea was just that I would oversee the sort of the physics and the math part to make sure that we weren't saying anything unreasonable. And then it sort of shifted over more and more to the physics and the math side. And so it really became a physics paper, and with a sort of acute mathematical result. So in this video, we're going to do the following. We are going to first review what the ontological model framework is, so that you know what the psi-ontic and psi-epistemics models are. We are going to show how we are going to break the model. We are make you aware of the cracks that this model have, and again, so that you can see when other types of models are too classical to be able to reproduce quantum mechanics. And then we're going to show, and that's the core of the proof, we're going to show that a psi-ontic model cannot replicate quantum statistical mechanics, quantum thermodynamics, and quantum information theory when we're just using standard techniques. And then, of course, somebody could argue, oh, but I could use non-standard techniques, and then these techniques do not exist, and we're going to mention some of the problems that these techniques would have to address. And then we also go back to the model, and we see how we can relax some of the assumptions to fix the model, to make it so that it's more quantum and therefore can replicate the quantum mechanics. Before we start, three disclaimers. We are not going to talk about specific interpretations. We're only going to talk about this categorization. I'm not an expert in interpretation of quantum mechanics. We're not going to talk about epistemic and ontological model in general. We are only going to talk about those that fit this particular categorization. So we're not ruling out that no ontological model can happen. We're only ruling out the ones that are in this categorization. And we're not going to talk about the philosophical implication. I'm not a philosopher. Ask the philosophers. I'm only going to look at the mathematical and the physical implication, the problems that are there in the math and the physics. So let's get started by doing a review of the ontological model. So what is that? So we start with the standard operational settings for quantum mechanics, which means that we have preparation protocols that are modeled with density operators, and measurement protocols that the most general is implemented with POVM, a positive operator value measurement, and these are a set of operators that have some particular properties, and each of them is associated with one particular measurement value k. And from the settings in quantum mechanics, we know that the probability of measuring k, given that we have prepared the system with preparation protocol P, and we're going to use measure protocol M, this is equal to the trace of rho ek. So this is the starting point. And if you look at the calculation, if you're not familiar with density matrices, what this boils down to is the probability, the expectation value of the probability calculated with the outcomes of the measurement and the probability distribution on the eigenstate of the density operator. So the probability distribution that comes in. Okay, hopefully you're familiar with this. Even if you're not familiar with this, it's not really so much a problem to understand the rest. What we do once we have this to get to the framework, we have to essentially add two assumptions. First is that there is an intermediate step. So we have a space of ontic state, and by ontic state it means some state that tells you everything about the system or the environment, everything about everything that needs to be understood to be able to talk about the system properly. And each element of the ontic states is an ontic state because, again, it tells you what the state of the system is really. And whenever we have a preparation, each preparation is gonna be a distribution over the set of these ontic state, and we call this an epistemic state. And already here there is an implicit assumption that this distribution characterizes a lack of knowledge. So the preparation actually prepared one thing, and then everything else will be determined by that one thing that the preparation actually prepared behind the curtain. Now, from the ontic state, we have to go to the actual measurement, and we do this with another probability distribution. So we are going to have the probability of observing the outcome k, given that we prepared the ontic state lambda, and we used the measurement protocol m. And we want this expression, of course, to replicate the result from quantum mechanics. So we need that this integral has to be equal to the trace of the operator, the expectation value calculated with the framework of quantum mechanics. The additional assumption is that whenever we mix epistemic states, so whenever we mix a procedure, we are going to use standard probability. That is, if P is a mixture of pure states with the probability given by these WIs, then the probability of getting lambda given the preparation P is just the weighted average, sort of the expectation of the probability. So we're just going to take the probability distribution for each pure state and multiply it by the probability and sum them all up. And so each ontological model is therefore characterized simply by the epistemic states that correspond to pure state, because all the other mixed states can be sort of created with linear combination from the epic states of the pure states. Now, if you are into math, you're going to have already seen that there are some technical imprecision here. There were probability where you should have done probability density. I'm not going to go through those details. These are typically glossed over in all these type of papers. I know they are important and they should be fixed, but I'm just following convention here and just use these objects as people typically use them. Okay, so now, since we said that each ontological model is fully characterized by these epistemic states for each for each pure state, the distribution over the ontic state given a particular pure state, we can classify the models based on some properties of these distributions. And so if we have distributions that overlap, that is, the same ontic state could be prepared by two different pure states, then we call these psi-epistemic models. And if instead all the probability distribution for all the pure state never overlap, then we call this a psi-ontic model. And this psi-ontic will be complete if there is one and only one ontic state per each pure state. And okay, so you might ask why these names, why do we call these like this? And to sort of understand this, we can make an analogy with classical statistical mechanics, and we consider two quantities, the energy and the temperature. Now, in classical statistical mechanics, the energy is a function of the microstate. If I give you the position and momentum of all the particles, you are going to be able to tell me what the energy is, because there is a well-known function. So, for example, this is the energy for a free particle. And so, depending where we are in the PQ diagram, the higher or the lower we are in P, the more the energy is going to increase. And so we have this temperature map where the redder there is, the more energy we is. Now, given that the energy is fully determined at the macro state, what happens is that the energy partitioned the phase space. So if I fix a particular value of energy, we're going to get a region of phase space where there are all the states that have that particular energy, and of course that region is unique. So different sets of constant energy are disjoint, and so if you had a uniform distribution of energy at a particular energy, you would have that this probability distribution would be disjoint. And by the fact that things are disjoint, you can really see that the energy is a property of the state, because it means that we must have a function like that. Now, if we take temperature instead, the temperature is defined on probability distributions, on a probability distribution at equilibrium, where we have a Boltzmann distribution. And so these will go like the exponential of minus e to the kt, or alternatively, you can define beta to be 1 over kt. This is what typically you do in thermodynamics, and so you have just one parameter beta that is nicer to handle. And so here we have three possible different distribution of probability given three different value of beta, given three different value of temperature. And what you can see here is that all these distribution overlap. In fact, if you take any state, this same microstate could be prepared by a macro state at different temperatures. So if I told you, oh, the system at this particular time is in this particular microstate, you wouldn't know what temperature it would be. You would have to see the system fluctuate a little bit, and then when you have enough samples and you can reconstruct the probability distribution, then you can say, the system is at equilibrium and it has this particular temperature. So temperature does not partition the phase space, does not partition the microstates, and so temperature is not really a property of the state, it is really a property of the distribution. So you can see that these two types of things that we have in classical statistical mechanics, things that are property of the state and things that are property of the distribution. Now, if we go back to the classification of the ontological model, if the distribution associated with a pure state, with pure states overlap, then it means that the same ontological state can be prepared in different way. And so really the wave function is a property of the epistemic state, like the temperature is a property of the distribution. And there is a theorem called PBR that rules out a large class of these epistemic models. It basically says, well, if these overlap, you can't replicate the probabilities that you would get with quantum mechanics. Now, on this other side, instead, we have the psi-ontic state, and as we said before, there is no overlap. This means that the wave function is really a property of the ontic state. If I give you an ontic state, you know what was the wave function that it was prepared with, and then this is like an energy. So therefore, it's really a property, the wave function is really a property of the ontic state, and therefore it's called the psi-ontic model. And so our goal is really to say something about this and to really to show that even this part of the model is also problematic. Okay, so now that we've seen what it is, let's ask a question. Does this work? Or there are some problems that we can use to break the model. Now, just to refresh, we said that we start with the operational settings for quantum mechanics, we add an intermediate step, and then we use classical probability over the epistemic state. And the question is, can this work? We're saying that we're using classical probability here, so it might be a problem. Is it a problem? Let's go and see. So at first look, if we assume that we have a psi-ontic model that is complete, meaning that there is just one lambda for each quantum state, then this would be the probability of transitioning from a particular initial pure state, initial wave function, to a final one, the one associated with k. So this is basically the inner product. So we could just hide the inner product inside here, and then we would just have a probability distribution over quantum states, and of course this is going to match this, so we should be done, right? So everything should work and we should be able to do it. Well, not so fast. There is still this issue that these epistemic state combine usually using classical probability. And this assumes that quantum statistical mechanics is simply classical statistical mechanics over the space of quantum states. And if you have ever studied quantum statistical mechanics, you know that that's not the case, that quantum statistical mechanics is different from classical statistical mechanics. There are some results in quantum statistical mechanics and quantum information theory that are really not replicable from classical statistical mechanics. So, for example, in quantum statistical mechanics, you can have multiple decompositions. So if we take probability distribution and we have one distribution, a probability distribution for z up and one for z down that are associated to our ontic state, and we sum them, these are necessarily going to be different than the probability distribution from z plus and z minus in the case that we are in an ontic and psi-ontic model, because these two distributions have to have disjoint support. All these four distributions actually have to have disjoint support, and therefore if we sum these two, they are going to have disjoint support from these two, and so they live on separate regions of the ontic space, and therefore they can't be the same. While in quantum mechanics, if you make an equal distribution of z up and z down, or x plus and x minus, you get the same maximally mixed state, and they are the same thing. So that those mixed states are exactly the same thing. There is an equality here, and the inner product is really what allows you to determine the equality. So the inner product is not just about measurement, is not just something that we use to calculate measurement, but it's something that we also use to calculate relationships between different preparation protocols. And this is actually one of the biggest misconceptions in quantum mechanics, is that quantum effects are about measurement. And this is something that also some people still teach, that the uncertainty principle is about measurement, and it's not really about measurement. There is consensus in the foundation of quantum mechanics that the uncertainty principle is about preparation and not measurement. And the uncertainty on the uncertainty principle is defined by the inner product. Therefore, the inner product is really also about preparations, not just measurements. Okay, but still, it seems here that we're going to be able to recover all the expectation of all the observable, right? And so this seems strange. We're saying that it's not enough, but we get all the observable, we get all the expectation value. So why is this not enough? Well, because quantum statistical mechanics and quantum thermodynamics depend on the thermodynamic entropy, which corresponds to the von Neumann entropy. The von Neumann entropy is defined on the preparation, right? It's a minus trace of rho log rho. It's a property of the preparation, and is not a Hermitian operator. There is no eigenstate of entropy. There is nothing like that. It's not an observable in the standard way of quantum mechanics, but we actually do measure the entropy, and we use the entropy to find distribution at equilibrium through maximum entropy and so on. And so we need not only to replicate these results if we want to get to quantum statistical mechanics, we really need to replicate the entropy as well. So each epistemic state must be associated with an entropy that coincides with the von Neumann entropy, or the model cannot recover quantum mechanics fully, because we can't do max entropy, we can do a lot of things that quantum mechanics does. And this is going to be how we break the model, not by looking at observables per se, but by looking at the entropy. And so, just to recap, the premise is that to reproduce quantum mechanics, one must reproduce all prediction of the theory, including those coming from quantum statistical mechanics, quantum thermodynamics, and quantum information theory. And now the issue is here that the ontological model assumes that statistical mixture in quantum mechanics are really classical mixture over the ontic state. And what we're going to see is that the degree of overlap between two epistemic states is linked to the entropy of the mixture of two distributions. If I have two distributions and I mix them and I look at how much the entropy goes up, Well, that tells us that that depends on the degree of overlap. So you can't decide what overlap you have. The entropy is already telling you how should it work. And so just by using simple standard information theory techniques, so things that if you are a third and fourth year you might have already seen, then we show that epistemic state must overlap, and therefore psi-ontic models cannot reproduce the correct entropy, and therefore they cannot reproduce the correct features of quantum statistical mechanics and quantum thermodynamics. Okay, so that's the plan, so let's just do it. And again, just to keep mathematically straight what are the pieces here. On the left side we have the quantum mechanics, so all the objects that we use in quantum theory. And on the right side we have these ontological models. We have the mathematical structure for that. In both cases we're going to have the space of mixtures, and in quantum mechanics is going to be the space of these densities operators, and on the ontological model is just the space of probability distribution over our ontic space. In both cases, we will need an entropy. And on the left side, because we're doing quantum statistical mechanics, we are going to use the von Neumann entropy, the minus trace of rho, which takes a density operator and gives us back a real number. On the other side, since this is the space of probability measure of classical probability distribution, well, the natural choice here is to use the tools of classical statistical mechanics, because we're doing a statistical mechanics using classical setting. And so in this case, the entropy, which is going to be this h lambda, is just the Shannon-Gibbs entropy, the minus of the integral of the p log p integrated over the whole space. And again, I want to stress that this expression is not really arbitrary. There is this is the only indicator of variability that is continuous, monotonous, and linear in probability. This is how the Shannon derived it. And we also have here a citation of a papers of ours in which we basically make that argument a little bit general so that you can understand in more different setting than what Shannon had in mind. So then for each quantum preparation, for each row, we should have an associated epistemic state. And then we should be able to calculate the entropy of the epistemic state. And we will need that this is equal to the entropy that we calculate in quantum mechanics using the von Neumann entropy. So we just do the calculation and see what happens. So the entropy of a pure state in quantum mechanics using the von Neumann entropy is 0. So we can just set that whatever this distribution is, the entropy calculated on that distribution has to be 0. Now in the psi-ontic model, the distributions are not overlapping, and so we can use that property to calculate the entropy of an equal mixture of two other probability distributions. And so if we just apply the definition, we are going to have minus the integral of the combined probability logarithm of the combined probability. And now we're going to use the fact that these probabilities are disjoint, so we're going to have the two subsets of the ontic space, u psi and u phi, and on this set the probability of lambda given phi is going to be 0, so the expression simplifies like this, and on the other set is going to be the probability of lambda given psi to be 0, and so it's just going to simplify like this. And now what we're going to do is take this logarithm that is a product of two things, and the logarithm of the product is the sum of the logarithm. So the first term is going to be the one that has a p, so we just remove this 1/2, and so the first part of this product will be 1/2 p log p, and that's just going to be with the minus in front the entropy of the first distribution. Here we're going to do the same thing. We break up the product. We're going to have 1/2 p log p, and this is going to be the entropy of the second distribution. And then we're going to have this logarithm of 1/2 in both sides that we can collect. In the middle we have the integral of p and the integral of p given phi. And we can simplify this by noting that the entropy of a pure state was 0. So this is 0, this is 0. This is just the integral of the probability over the whole distribution, so this is going to be 1. This is by the same token is going to be 1. So you have 1 plus 1, 2, divided by 2 is 1. So you have minus logarithm of 2. And you can minus the logarithm of the reciprocal. So we're going to have plus logarithm of 2. And since our logarithm are going to be in base 2, logarithm of base 2 of 2 is going to be 1. So the entropy of an equal mixture of two states, if we calculate it over a psi-ontic model, has to be 1. Okay? And so, in a psi-ontic model, the equal mixture of any two pure states correspond to 1 bit of entropy. Now, the problem is that if you do the same calculation in quantum mechanics, it will depend on the inner product. This calculation is a little bit more involved, but there is a link to the paper down if you want to look at it. There is the appendix, it has a nice diagram and you can follow it. If I might even be able to do a different video of that, because this is a sort of a general result that it's kind of neat. But anyway, if you do the von Neumann entropy of an equal mixture of two pure states, you get this expression. You recognize that this is another P log P, and this is another P log B. So this is really the Shannon entropy calculated over the two coefficient, 1 plus the square root of P over 2 and 1 minus the square root of P over 2. And you can see that if P is equal to 1, that is, you have the same state, because this is going to be 1 only if the two states are the same. You're going to have 1 plus 1, 2. So you have 2 log, actually 2 over 2. So this is 1, logarithm of 1, this is 0. And then here you're going to have 0 log 0, that tends to 0. So all of this expression is going to be 0, which makes sense because we saw that if you only have one state, the entropy is 0. And if the two states are orthogonal, then the probability of transition is 0. So you have 1/2 logarithm of 1/2, and here you also have 1/2 logarithm of 1/2. And if you do the calculation, you just have 1. So this entropy is going to be between 0 and 1, with 0 when the two states are the same, and with 1 when the states are orthogonal, when they are completely distinguishable. But we said before that in psi-ontic state, it can only be 1. In a psi-ontic model, then all the states are absolutely distinguishable, which is what happened in classical statistical mechanics. In classical statistical mechanics, all states are distinguishable. There is no states that overlap in some way, or the points are distinct points. And this is how we get to the no-go. So if we use standard information theoretic technique on these things, we're not going to be able to replicate the result, because the degree of the overlap between epistemic state is constrained by the entropic structure of the mixed states. Okay, and one might say, well, couldn't we simply use a different formula for entropy instead of the standard one? And sure, but you have to provide one. You have to create a whole new framework of doing statistical mechanics. You have to create an alternative framework of statistical mechanics on top of classical states that gives you back quantum mechanics. And this is hard. Like, we don't have one. If we had one, there would be no issue on the foundation of quantum mechanics. So you can't just simply say, oh, we can use another one. You have to show, you have to prove that one exists, and that you can use it for doing maximum entropy techniques. You can use to do the similar thing that you would do when you calculate eigenvector and eigenvalues of a density matrix, because also those things are important for quantum statistical mechanics and so on. And so I'm not saying that this is absolutely not possible. I am very, very skeptical. So I'll tell you some of the problems that you're gonna find if you try to do it. So first of all, the entropy is strictly concave, meaning that if you take two different states and you mix them, the entropy goes up. And if it doesn't go up, it's just because you have the same states. So the entropy does not go up if you're just mixing the same thing. If you mix something different, the entropy will go up. And here's the issue, is that the same density operator can correspond to different classical mixtures, because as you saw before, in quantum mechanics, you can have these multiple decomposition, and this multiple decomposition will correspond to different epistemic states. And so if you mix some of those different epistemic states, that correspond to the same density matrix, even if though it's a different classical preparation, the entropy is not going to go up in quantum mechanics. And so you're going to have a problem here, because if you're trying to create a framework that maximizes entropy, and the entropy is not strictly concave, it makes it a lot harder. If it's strictly concave, it's very easy to prove things. If it's not strictly concave, it's good luck. You have to have something else. So there is a big technical problem there that you have to figure out. But then suppose that you solve this and the million other problems that you might have, such as that the entropy is finite for distribution on finite and infinite states, or that the entropy encompasses the system is going to have other things that are weird in quantum mechanics that are not replicated in classical mechanics. Suppose that you're able to solve all of that. You still have the problem that essentially the calculation of the entropy requires the inner product. So the inner product must be hidden in both the probability of transition and the thing that calculates the entropy. So it's not as nice in the model that you say, oh, okay, we have our ontic state, and then the Born rule only comes in for the transition. No, there is something that you have to do at this ontic epistemic level to make more sense of what's going on. And I think still that might give you something that you didn't want in the first place, and it's going to give you something a lot more complicated. Okay, so we saw that the psi-ontic models are problematic, but as we said in the introduction, there is this other theorem called PBR from the initials of the author of the theorem, that shows that psi-epistemic models are ruled out. Well, not all of them, the one that assume independent preparation. So we have this big class of models that are ruled out. We ruled out a bunch of other models, and so the only ones that remains are the psi-epistemic models that do not assume independence. The issue is that in the same way that the entropy knows about the overlap, it knows about the independence. The entropy is subadditive. If you have the two systems and you put them together, the entropy is going to be the sum or less of the entropies of the individual system. And you're going to have an equality, you're going to have the sum if the two systems are independent. And so you're going to be able to use this to construct as an argument that works similarly to what we use to rule out the psi-ontic states, because you're going to have some cases where you would want things to be not independent, but the entropies tell you that the systems are independent because the entropy is additive, and you can use these to create some problems. So basically what happens is that no ontological model can really reproduce quantum theory, and again, no ontological model that fits this narrow definition that we saw before. So why is it? Why is it that you have this problem? And the problem here is that the ontological model is simply too classical. We have these assumptions that we saw before that makes it such that any ensemble that you have in the ontological model is really a classical probability distribution, and a classical probability distribution is not able to give us all the results that we have in quantum statistical mechanics. At least this is what we think is going on here. And so what you can do is just go back and look at those assumptions that you put in and try to remove them, try to reason about them and see if you could do something different. So the first assumption was that we were adding an element here in between. And again, this had the implicit assumption that the distribution is characterized by lack of knowledge and everything depends only on one sample. But if you remember when we talk about classical mechanics, this is not even true in classical mechanics either. If I wanted to know what the temperature was, then the temperature is not really something that I can understand, measure by looking at just one instance of one microstate. I need to get the full statistical distribution. So, if we were trying to get a temperature-like quantity from this distribution, we wouldn't be able to use this. We would be able to have something that depends on the whole distribution and not at the distribution sample by sample. And so if you think about that the quantum states are fluctuating and the wave function is telling you how things are fluctuating in some way, then you are not you're not going to want to have this division. And so you can keep the linearity of the distributions. When I create these distributions here, I can still make these epistemic states linear, but then when I make the measurement should not depend on just one sample, it should depend on the full distribution. And so the expression is going to be a lot more complicated. So that would be a way to sort of say, okay, let's relax this assumption and see if something else would work better. Now, the other one is the other assumption that really gave us classical mixtures, classical ensembles on the whole ontic space was the use of classical probability over the epistemic state. So if I have a statistical mixture of preparation, then we are just using a weighted average of the probability distribution. And this brings in classical probability because we have this additivity. And again, there are already results in classical probability theory that we cannot replicate quantum probability, but there are extensions. So for example, we could sacrifice the non-negativity of a probability. We can have probabilities that are negative and keep their linearity. And this is what leads to quasi-probability distribution, things like the Wigner function, if you haven't heard of them. So there is a way to do quantum mechanics on phase space with things that kind of look like probability distribution that have expectation values, but the probabilities can be negative. And of course, you might not like that probability is negative, because what is a negative probability? I have personally no idea. Or one of the things that I've been starting to look at, we can try keeping non-negativity, but then we sacrifice the linearity. There is going to be something more complicated that goes on when we prepare mixtures of preparations. And again, so this might give you something that might be more interesting to study and so on. And so that's it. I hope that they gave you a little bit more of an understanding of what these psi-ontic and the psi-epistemic model, if you haven't heard these terms, I hadn't heard them before I started working on this paper 3 years ago, but then again, in some circles, these are what everybody talks about. So I hope this was useful to you. If you have questions, you can leave them at the comment. And if you found this interesting, you can look at the rest of my research on my website, assumptionsoftphysics.org, other videos on this channel, and I'll see you in the next video.